invited me to speak. So today I will talk about the geometry of Croke-Kleiner admissible groups. This class groups was introduced by Croke-Kleiner in 2002. This class groups was modeled on the fundamental group of graph manifolds. So my talk will consist of 3 parts. In the first part, I will give you an introduction to this class of groups, introduce the definitions and examples and some problems I want to address in this talk. Then I will talk about the rods. The rods will be joined with Hoang Nguyen from University Da Nang in Vietnam. Finally, in the last part of my talk, I will discuss some ingredients in the proof of our measure rods. So, as I said, this class group is some generalization of graph manifold groups. So I start with the introduction of graph manifold groups. So the graph manifold is by definition just admits some non-trivial geometric decomposition, such that every component admits self-separation over a hyperbolic two-orbifold. Yeah, there are several definitions. It's just one definition is convenient for my purpose of this talk. So by this non-trivial geometric decomposition, I mean there's a minimal family of geodesic minimal family of tori, such that the complete amount of this tori are self-fabrications in this case. So here, for instance, we have probably I made the cartoon give you some picture of what the graph manifold looks like. Okay, there's some piece from here. These are separated by some tori. So each piece will have some fibration. This is called self-separation. This means maybe there are more pieces. Yeah, then maybe you can close here. So for each piece, here they just roughly you can think of these circle bundles over surfaces. For instance, here we have a surface. We have two boundary components. This is sigma, and we have a fibration. This is a bit complicated, but here we can up to some finite cover. You can just suppose this fibration is a circle bundle over surfaces. So it looks so just the times of S1 cross these surfaces. So for each one we have such structure. So by this fibration you have this exact sequence. This is Z just the fiber that represents the fiber of this self fibration, and here we have these surfaces. And this Z is central in this self fibration, this self manifold. So we have this exact sequence. So this is roughly what a graph manifold looks like. So Croke-Kleiner groups just generalize this picture to in more group structured way. So a Croke-Kleiner admissible group. This is just a graph of just a graph of a graph of groups, such that the following properties hold. The first, this graph of groups is a space over the abelian group of rank 2, just the abelian group. Because in the graph manifold group, this this the torus has a fundamental group Z2. So each vertex group here we make an analog with the separation. We assume each vertex groups admit central extension. Just we have this exact sequence. But here, this is different from graph manifold groups. In graph manifold groups, here we always have the fundamental group. This is a free group. This is just free group. But here we can allow this to any possible non-elementary hyperbolic group. Then the second condition is just for each edge we have for each edge we have for each edge for one vertex we have this this center of this vertex group, and we have the other center of the vertex group. We assume these two centers, each is a cyclic group, but we require their generates a subgroup RAC2. This means it's a finite index in the edge group. These centers, just as I said here, these centers represents the fibers. So here, this means. So here, maybe I take another. I draw the picture here. This is for the onto another self-manifold. We have here. We have maybe we have 4 boundary components to the space surface, and we have the S1. This is fiber here. So because in the geometric decomposition, I assume this is a minimal family of tori, such that we have these properties. So each component has this self-fibration. So here, this we require this fiber. For instance, this is a fiber for N2. This is fiber for the N1. These two fibers should be not parallel. Otherwise, we can glue, we can combine, we can delete this tori, just combine this to take the union of these two surfaces. So we don't want the fiber to parallel. So this second condition just makes this explicit. We require the setter groups generates Ionic group of RAC2. In other words, just finite index in the edge group. So also there are another conditions. If for each vertex, there's two for any two edges. For the E1, this is E2. There's two edges. We assume the edge group, are not commensurable. Or if this is true, then if this is commensurable, that means the E1 and E2 are equal. There's the same edge. Okay, let me unfold this definition a little bit. So here, because as we see this in each, we have the center group. This GV is length is contained in the edge group G1, also contained the edge group in the conjugate of G2, because this is the center. This is the center. This is a center group. This is a center in GV. So of course, this contained in these two groups. So here it's not commensurable. This means this should be is a finite. This should be this is not commensurable. This means this should be this is a finite index. This is a finite index. This center group is a finite index. This in sections, because each edge group by definition is just the Ionic group of RAC2. So the center group is so this is equivalent to say this center is finite index in the intersection of these two groups. So if you project these groups, because let's denote the constant group constant map pi from GV to HV. This means so we collapse this centers. So we have this two group. Should be so this should be finite. This should be finite. This should be finite. Or this should be these two edges should be the same. In this case, the G is inside of the edge group. So in some words, what I said here, if you project this these edge groups into the constant group HV, this should give you a mononormal collection of subgroups, cyclic groups. So this means this. So if we project to this consider all the edges adjacent to V, project to the constant HV, this should be mononormal family of subgroups. So this is the property what this condition says about this class about the relations between the edges. So if you project this edge groups into the constant group, this should be mononormal. This means the two conjugates should be intersect in a finite group or the same. Okay, this is roughly the definition of Croke-Kleiner group. This is modeled on the graph manifold groups. The third condition just means you don't glue glue the same boundary. You don't glue two self-referred manifold on the same boundary. So you don't do this. You don't do this. So you just each boundary component you attach one. You don't glue two self-referred manifold on the same boundary component. Any questions about this? Yeah, this might be a little technique, but this is just see just try to see the same thing as the graph manifold graph groups shows. Okay, so some general facts about the Croke-Kleiner admissible groups. So by the definition, the graph manifold groups, just the Croke-Kleiner admissible groups. Just by this definition, we have the GSG, this geometric decomposition. We have this graph of groups. So we have this just the Croke-Kleiner admissible groups. Also, the asymptotic dimensions of CK groups are finite. This is because each because this follows a rod of these two matrices. This rod of set the rod says that if a group is a graph of groups such that each of text groups has finite asymptotic dimensions, then this graph groups has finite asymptotic dimensions. Because here the text group are the integer group crosses hyperbolic group, so they have a finite asymptotic dimension. Also, another interesting rod about the CK groups is the follows. The action of a CK group on the Basel tree is 3 asymmetrical. This means if you consider the segment of 3 edges, then the stabilizers of this 3 edges will be trivial. So this shows this group is a cylindrical hyperbolic in the sense of ocean. Okay, the CK groups turn out exhibits many exotic behaviors. For instance, the first example of immersed closed surfaces in graph manifolds, which are not liftable as embedded ones in infinite covers. This is first constructed by Robinson Wang. So this gives some non-separable subgroups in first examples of non-separable surface groups in graph manifolds. Also, this gives the first examples of KZ groups such that their boundaries are not homomorphic. It turns out these groups are very simple. The construction of these groups are very simple. They just take three torides. Three torides. So we make the following identification. So we just glue the toride along this circles according to the color. So here I take. So okay, this two we don't glue these two colors. Okay, maybe I take a different color. Okay, this is so yeah. Just we glue. Okay, maybe I take still take same color, but we glue these two are the same. We don't glue the. Okay, maybe I take another one. Sorry, take another color. Okay, so I take a different color. So we glue this three tora together. So we have this. Okay. Here we take the S1 glue on S1. Here we glue on the black circles. Okay, so this turned out the Croke-Kleiner admissible group, because here we can just take a figure 8 here. Sorry, that's not figure 8. This yeah, figure 8. Here we should take black color, and here we have. Sorry. So we take a cross of this figure 8 with S1, and this side we take okay, I take the random one. So we take this will be yeah, this will be just the cross of figure 8 and S1. This figure 8 S1. Then we take the then we glue along the boundaries along the boundary tori. So we have yeah, just we glue here. Just we glue here. So it turned out this is a Croke-Kleiner group. We take this free group across S1 across Z and free group across Z. We get this this example of Croke-Kleiner. So this examples show some exotic behaviors of CK groups. But in this talk, I will focus more some more regular, more positive behaviors of these class groups. So from this construction of this Croke-Kleiner groups, in fact, this we have some recipe to construct CK groups with some flip condition. Just the model on this example, we can start from any graph with vertices labeled by 1003 hyperbolic groups. Then we have okay. Let me make some cartoon here. we just take any graph with vertices labeled by some hyperbolic group. Then for each edge enter into this vertices, we choose a set of maximum cyclic subgroups, which are pairwise non-conjugate. This otherwise, in other words, this is the same as these groups. These groups should be mononormal, as I said before. It's a mononormal. Just the intersected trivial is mononormal in HV. So for each we have choose for each edge we choose these elements here, E1, E2, and for here we also choose this. We take the opposite. We have the inverse of image. We take the B2 in this side, and we construct. So we choose such a set of maximum cyclic groups. Then we can get CK groups. Just we take because the CK groups require each vertex should be product of a hyperbolic group with some cyclic group or some central extension. Here we just take this direct product. So in this case, we just for each vertex group, we just choose a fiber group, take the product, and we have we have for H1 and cross FV, and we have the other vertex group HW takes the fiber FW. Then we take them, glue them together. So here we have edge group. Edge groups here we just take the flip relation. This means we take just request the FV equal to the boundary group of the adjacent vertices. At the same the edge group, the boundary group of HV is equal to fiber group of the W. So we just do the flip trick. So we get this graph of groups. So this is just a very flexible way to construct CK groups, satisfy some flip conditions. Okay, any questions about this construction? Yeah, you can just start any graph with some hyperbolic groups aside to each vertices. Then you can build a CK groups. Okay, so now we have some questions about the CK groups. So these questions are in line with the study of graph manifold groups. First, we want to understand the properties of subgroups of CK groups. For graph manifold groups, the people understood well the separability of subgroups and the distortion functions of subgroups, and also the strong quasi-convexity of subgroups in CK groups. So in our talk, we will consider a generalization of this route to general CK groups. Also, the second question we can ask, we can try to give some quasi-isometric classification of CK groups in terms of the quasi-isometric type of hyperbolic groups, because we can build from any set of hyperbolic groups, do this flip trick for instance. But also this in general this shouldn't be enough, because we also need to take care of how we choose this set of cyclic groups, or we can see what's the symmetrical patterns of the boundary lines in each hyperbolic groups, how to glue them together. So this possibly some data you need to classify give a quasi-isometric classification of these class groups. In graph manifold groups, this is already done by Stock and Nguyen. So we can do some routes in this direction. I want to describe some progress in this direction. Okay, so now let me start to introduce our first route about the subgroups of CKD groups. This is about strong quasi-convexity of subgroups. So we see a subgroup is strongly quasi-convex in a group G. We always assume group G is finite generated and H also finite generated. So if it's called strongly quasi-convex, if for any quasi-convex, any lambda C quasi-geodesic with endpoints in H, it stays in a uniform neighborhood of H. Then we see this H is strongly quasi-convex. This notion that depends on the choices of Cayley graph. Just for some, in fact, for any, because we require for any lambda and C. So these different Cayley graphs are quasi-isometric. So we have this definition that depends on the choice of Cayley graphs. So it's some interesting notions of this subgroup. So the first route of this talk is the following. Let's consider CAT0 Croke-Kleiner Admissible group, and also finite generated subgroup H. Here I assume this is CAT0 because in the Croke-Kleiner group there we only have a central extension. If we have a CAT0 condition imposed on this group, then this implies this central extension is virtually direct product, because the central extension of CAT0 group, which are central extension, must be a virtually direct product. So virtually is a hyperbolic group cross Z. So in general, once we have this, then we have the same conclusion. So the CAT0 mainly for this property. So then we can characterize strongly quasi-convexity of a subgroup as the finiteness of H. The finiteness of a subgroup, this means the following conditions. This some kind of algebraic conditions. This means we can consider any n distinct conjugates. This means this left coset are different. So this means a different distinct conjugates. So if you take any distinct conjugates of H, the intersection of them should be finite. So this is some kind of opposite of normal subgroup. If normal subgroup, it should be the same. If H is infinite, then an infinite normal subgroup will never have finite height. Yeah, so if also the infinite index. So this is some kind of algebraic conditions imposed on a subgroup. So here, we prove this is equivalent to geometric condition imposed this class groups, this subgroup. So in particular, as a consequence of this finite height, any such strongly quasi-convex subgroup must be virtually free. So this is a very restricted way, very restricted class of subgroups. Okay, this is the first route of our talk. So let me introduce the second route. Before that, I want to give some motivation of our route. This is a theorem of Bastvina, Bromberg, and Fujiwara. They proved any residually finite hyperbolic group must act properly on finite product of quasi trees, such that the orbital map is quasi-isometric embedding. Here, acts properly, it just means this in a metric sense. This is just for any metric ball of radius r, you only have finite many elements, such that it translates of the ball intersect itself. So this there has some in a metric sense, not a topological sense. So in fact, here this quasi tree is you can't be improve the quasi tree to a tree. Quasi tree means just a metric space is quasi-isometric to a separation graph. So in fact, a hyperbolic group with a Cartesian property must act trivially on any tree. So there exists residual finite hyperbolic group with the property T. So we couldn't improve this quasi tree to trees. Also, we have a generalization of this class, generalization of this rod to the more general class of residually finite relatively hyperbolic groups recently. So there's some relevant rods here I want to mention here. So now let me state our second rod. Here, let's consider again. We consider KZ CK group. Now we assume this we have flip condition. Just you can imagine the groups is constructed as I just explained. Then G, this group G must act properly on a finite product of non-proper hyperbolic spaces. Moreover, if every text group has omnipotent hyperbolic quotient, because each text group have this central extension. So here we assume this hyperbolic quotient should be omnipotent. Omnipotent, this notion introduced by Daniel Weiss, it includes, for instance, you can think of these free groups and three manifold group, hyperbolic three manifold group, or more generally, you can consider the virtually expansive hyperbolic group. So these are all omnipotent groups. So if every text group has omnipotent quotient, then the group G turn out to act properly on finite product of quasi trees as the hyperbolic group case. Okay, now the other rod in terms of the quasi classification of CK groups, it's we can prove that it's a this work progression in progress. Any CKA CrokeKleiner group is quasi-isometric to a CK group with flip condition. Just as we said, here in this prover theorem, we need to put a CK. We need to put a flip condition. This is very crucial in our proof. But in general, if you consider a general Croke-Kleiner admissible group, which might not be flip, will not without a flip, possibly without a flip condition. But in other ways, you can always get a construct quasi-isometry between a general CK group to a CK group with a flip condition. So the classification of CK groups is used to CK group with a flip condition. Okay, this is just some progress in towards this quasi-classification of CK groups. So, any questions? Okay, even then the question. I want to give you some ideas and the ingredients of how these two rods I mentioned is approved. So let's focus the graph manifold groups. So because we consider the cross geometry of these groups. So let's look at the universal covering of this graph manifold groups. So because the graph manifold, these all CK groups are graph of groups. So the universal cover or the K graph of the CK group is has some kind of tree of spaces structures. So the underlying tree, just the Basier tree for this JC decomposition of a manifold, or you can think of this CK decomposition there. And if for the graph manifold group, so for each vertex, group, for each vertex manifold, there's pieces, the self manifold. So the universal cover of a self-read manifold is just a convex subset of a hyperbolic plane, because this is with the boundary. So this is a convex subset. This is universal covering of this surfaces with the boundary. And we let's cross the R. This is the fiber direction. So the universal covering of this graph manifold, just a tree of spaces. Each vertex, just the direct product of convex subset with R. They are glued along this Basier tree. So here, for instance, we just consider this example. We have two pieces, two separate manifold. We glue them by this flip V. This just the fiber is identified with boundary as the picture shows. So now the universal covering, you just I colored the universal cover of each vertex, each pieces. So for instance, here we have so we lift this manifold to here. This the R cross this convex subset. So it's have the structure. It looks like this. And for each boundary component, we have a boundary plane here. This adjacent the adjacent self manifold. But here the point here we have the fiber direction here. This two fiber direction, as explained earlier, they are not parallel. They're not. They should have some. They shouldn't be parallel. So for instance, here they have they are orthogonal, because we take this flip condition. We just swap this two swap the fiber and the boundary components. So we have this picture. So this is the picture of universal covering of a graph manifold. So now we want to construct a class of group invariant of quasi-geodesics between any 2 points. So this we rely some notion of CrokeKleiner. It's called a taplet. A taplet is just the KZ space obtained from a disjoint union of walls, just the Euclidean plane in dimension 2, and strips. So that just as the picture shows, so that any two strips attached to same wall are along non-parallel lines. In fact, this will be the fiber direction. This will be the fiber. This will be fiber, as the previous picture. This will be fiber direction. This boundary plane will be just the boundary plane here. This is fiber, just the this strip, just the direction of strip, just the fiber of the self manifold. So this is just a KZ space. You can take a disjoint the walls and glue them in this way, in this non-parallel way. Then we want to understand. For instance, we take 2 points, X and Y. we want to understand what's the geodesics between them. So the geodesics you must be travel in each strip, and when across this wall, you may have you may cross in this way, then continue. We have geodesic in each strip. From here, you get to here, you travel to the yellow strip, then you continue, and to here maybe you travel some time in this boundary plane, then to this red strip, then you continue. Okay, this may be the shortest geodesic. But it turned out we can choose some canonical paths between any 2 points, such that they're not geodesic, but they are called geodesic. So this this path we call spansel. This can be written as a sequence of geodesics. So as this template shows, any 2 strips intersect in the unique point on each boundary plane. So we can just connect this intersection point by geodesic segment. We get this path. This path turned out is called geodesics. It's very easy to verify. It's just you can consider general geodesics. Then you just possibly it doesn't pass through this intersection point. Maybe it goes in this way, but you can just push this geodesic to this point. You can cancel this geodesic triangle. Then you don't increase the path too much. So the consequence of this definition give you the spansel paths are uniform cogeodesics. Now we can see this spansel path somehow is canonical because because in between this path it not depends on x and y. So for any 2 x, y you choose here, x prime, y prime. So in between this will be the same. So if you take a very long path, so basically only the study points, the initial part, this two block, you may the 2 blocks you may vary the path in these 2 initial blocks, and the terminal 2 blocks in between, in the middle, you don't change anything. So this spansel path is somehow very canonical. So use this spansel path, we can prove the first route that we can prove the strongly quasi-convex. We can prove if a subgroup is finite height, then this subgroup must be contracting in some sense, contracting with respect to this family of paths. So this proves the first route about the strong convexity of subgroup. Now let's go further. How to prove the second route? So in this case, we need to construct action on some products on some finite products of hyperbolic spaces. So how to get hyperbolic spaces? So the way is to first partition the vertex set of the Basel tree in 2 disjoint parts. So we just glue. First, we consider the previous case. We have only 2 pieces. We just consider each vertex set. We want just consider the consists of the vertices such that they have pairwise even distances. Just we choose the vertex alternatively in this way. So yeah, just as this picture shows. So then we can construct these hyperbolic spaces, just because because this will be because this for each adjacent, for each neighbor neighbor vertex fiber pieces, you have a hyperbolic convex subset. The boundary won't be parallel in the middle one. So if you look at the picture of I draw here, we try to glue this three red one universal covering of this these surfaces. So this boundary is parallel. This boundary line, it coincides with the fiber line in the middle one, because this is just a flip condition. So we just glue them together. They're parallel. We can glue them together in a natural way. So this you do this construction on each vertexes. So you get two hyperbolic spaces. So this give you a hyperbolic space because it glues in a tree-like way. Also, we have an action on this product of these two spaces. Moreover, you can show that this induced map is quasi-isometric embedding. It's just you can think of this picture. You just project this spatial path to the base hyperbolic surfaces. In fact, this decompose this spatial path into two passes. Each pass is in this base, in hyperbolic base surfaces. So you have this map is called isometric embedding. So finally, if we want to improve the hyperbolic spaces to quasi-tree, because quasi-tree somehow is the most may have more good properties than general hyperbolic spaces. In this, if you want to improve the hyperbolic spaces to quasi-tree, so this is follow some argument. The Bastavina, Pornberg, and Fujiwara. So as proof of hyperbolic groups. So for each we can construct for each hyperbolic basis surfaces, you can construct a finite set of logarithmic elements. So you can construct a finite family of quasi-lines. Also of subgroup of finite index in this surface group. Then we can use we can construct this finite set of logarithmic elements such that any two points can be approximated by this quasi-lines. So once you can recover the distance from each hyperbolic surfaces. Then you need you use the Bastavina, Pornberg, Fujiwara's projection complex. We can produce fundamentally correlated trees from this logarithmic elements, this quasi-lines. Somehow we glue these quasi-lines in a tree-like way, so that we get these quasi trees. But finally, we need glue this family of subgroups to get a subgroup of the whole subgroup of finite index in the whole group, so that this G acts on these quasi trees. Okay, I think okay, this is maybe a bit too technical here to explain this. So okay, so I will stop here. So thank you very much. If you have any questions, I can explain. So I will stop here.